Lesson 2.3, we're continuing on with rates of change. This time we're going to focus just on using graphs. This is a tangent line. Remember, a tangent line touches one point of the graph, a secant line touches twice. We know that the average rate of change of a function over an interval can be measured with a secant line. Secant line is average rate of change. It goes through 2 points on the function. But if these 2 points are far apart, like on this example here, the slope of the secant line wouldn't be a good approximation. So see this red dot here? If I needed to find the slope of if I could draw a tangent line right there, just touching the red point here, this secant line is not necessarily a good estimation of the same one. So if we have points that are really far apart of the point in question, secant line is not the best way to go. So we get more specific by finding the average rate of change. We look at smaller and smaller intervals. We want to get closer and closer to basically this red dot here, which means that delta x, the change in x, approaches 0. We are hardly having any distance between our point in question and a point beside it. We use preceding and following intervals, centered intervals, squeezing intervals. The difference quotient helped us to approximate the instantaneous rate of change. So this is all summary what we're talking about here so far. So here is another secant line, the blue one, but it's a lot closer to that red dot. So it's a better approximation because we get smaller and smaller intervals between x2 and x1. Our 2 points where it touches the red curve are getting closer and closer together. On a graph, the instantaneous rate of change of y with respect to x can be interpreted as the slope of a tangent line. So instantaneous means the tangent line. The tangent line is a line that touches the graph at only one point within a small interval. So if you look over here, this is a tangent line here. Now it does cross again over here, but in this area of concern right here, it's only touching once. It's skipping off once, like a stone skipping off the surface of the water. So it may cross again later, but close to its point, it's only once. And then P is called the point of tangency. So here's a little animation of a tangent line. So this tangent line is touching each point of the red cubic all the way around. So the tangent line is telling you the slope at that exact value. So right here where it's frozen, that would be the slope on the cubic. It would be the rate of change right at, say, that's maybe a value of 1, x value of 1 or close to 1. Example 1. An antiseptic spray is applied to a culture of bacteria. The percent of bacteria that are alive after time minutes is shown on this graph. A secant line has been drawn through the points T5 and 35. So here, this blue secant line goes through, the red one is the curve. The red one is the curve of our function, the percent of bacteria against time. And then the blue one is a secant line. The green one is a tangent line. So it's been drawn just through 20 out. It almost looks like it overlaps, but if we zoomed in, we would see that it wouldn't. We need to calculate the slope of the secant, that's the blue line, and then we're going to describe what it means. So remember, a secant line is just a slope formula. In this case, we're looking for the change in the percent of bacteria over change in time, delta B over delta T. We sub in the coordinates that were given to us right over here, 580 and 3526, and we get negative 54 over 30. That's the same as negative 1.8. So the slope is the average rate of change between the percent of live bacteria between 5 and 35 minutes. So in that time frame between 5 and 35 minutes, on average, this is the rate of change. And this says explain the sign of the slope. The amount of live bacteria is decreasing at a rate of negative 1.8. Now I said decreasing, I didn't have to put the negative in, it's kind of redundant to put them both in, but I just wanted to be clear here. We have a negative value, and that means we have decreasing. And our slope, remember Mr. Slope Guy, our slope is coming down. So that's why it's a negative value. So the live bacteria, of course, is decreasing because it's had an antiseptic spray applied to it. So over that 30-minute time interval, we've got a decreasing amount of bacteria percentage. Part B, estimate the instantaneous rate of change B with respect to T at 20 minutes. So we're still looking at kind of this important value of 20 minutes right here. Note, it is very hard to draw an accurate tangent line by hand, the green one you see here, unless it's drawn for you, as it is in this example, or unless a question specifically asks you to use your own tangent line. You can't use this method. It's never good enough. However, if it is drawn accurately, the tangent line is better. It's a better calculation of the rate of change than a secant line is, because a secant line crosses twice, a tangent line only once. So we're looking for the slope of the tangent line at t equals 20. Right here, we're looking for the slope of the green line. Find two coordinates on the green tangent line that we can use in the slope formula. So we're looking along the green line to find two nice coordinates. We'd rather not have to use decimals or anything like that, but we'll do the best we can here. So of course we're going to use 2043, and the other one that looks pretty clear is 4010. So this spot right here, it's not exact, but it looks pretty good. This is why when we have to draw a tangent line or use a graph, we're introducing a certain amount of error. This time, this is an instantaneous rate of change because we are talking about a tangent line, not a secant line. So it's an instantaneous rate of change. Same formula, we've got two coordinates, we sub them in, and we get negative 33 over 20. That's negative 1.65. So that means the amount of live bacteria is decreasing at a rate of negative 1.65 per minute at 20 minutes. So this answer is more accurate than this answer here. The first thing I want to point out here is this notation here. M means slope, and this little subscript just tells you what you're finding the slope of. So the slope of the tangent line is called an instantaneous rate of change. But if you're looking for the slope of a secant line, that's an average rate of change. Example 2, graph this function. So there's more instructions here, but we're going to start just with graph this function. And this is an exponential function. So let's get to work by remembering, first of all, this is the parent function right here, but then it's dropped down 3. So I've already got my axes in place here for where I need them to be, and I'm going to put a scale on there. So I've got my scale on there. Now I'm going to draw my function. It's the parent function dropped down 3 units. So hopefully you are pretty comfortable with that parent function, and you can graph this quickly. If not, you can sub in values. So I could sub in, say, f at 1, and that would give me 2 to the power of 1 minus 3. So that's 2 minus 3, which is negative 1. 1, negative 1. And I could keep going on like this to get coordinates. It will take a while. One important part for you to remember is that minus 3 value right here, that is your horizontal asymptote. So you need to get your ruler and draw a horizontal asymptote in straight across the y value of negative 3. So I've got a few more points on here and my asymptote, and I'm just going to try to draw a smooth curve connecting them all. That's getting kind of bumpy there. And of course, for the asymptote, I do not cross it. I'm going to run alongside it, kind of above it, getting a little bit closer all the time, but never actually crossing it. So that's my f at x. That's the first part of the question. The next part says, draw 2 secant lines that you could use to estimate the slope of the tangent when x equals 2. So when x equals 2, this is our important value here, 2, 1. trying to find the rate of change of this function right here. So we're going to draw two different secant lines. So a secant line has to pass through two coordinates there. So let me just switch colors here. Let's say I'm going to pass through 3, 5, and this one here, 1, -1. I'm putting green dots there. So I'm going to draw a straight line through those two. The reason I'm picking those two is because the x values are equidistant from the x value of 2. So I'm going 1 unit to the right of 2, which is the 3, 1 unit to the left, which is the 1. So here's my first secant line here, this green one. So we're going to use that. That's going to be secant line number 1, and we're going to use it to estimate the slope of the tangent line when x equals 2. So we're going over to our formula under secant line number 1. We're looking at the change in the y's over the change in the x's. So I have to find two coordinates on my green line. I've got them here. And I'm going to sub them in to the formula. So y2 minus y1, that's going to be 5 is my y2 minus my y1 is -1 over x2 minus x1. That gives us 6 over 2, 3. So there's one secant line. That's the slope of that. So the slope of this green line here is 3 units. The next part of the question, well, we've done the part that says 2 secant lines. So we've got to do another secant line. So now I've got to find another 2 points, maybe a little further apart or maybe a little closer together. I'm just going to use another one here. So let's find some values that are further apart. Let's go a little further apart to see what happens here. All right, to go further out, my next point, 413, would be off the graph here, so I just put it above here. So 413 I put in blue, and 02, that's both 2 units away from the point in question here, which is an x value of 2. So we're going to go 2 units away from that on the red graph, draw a blue line through those, and we will have our second secant line. So there's my blue one. Put some arrows here and here. That's my secant line number 2. Let's go over to our equation for secant line number 2. y2 minus y1 over x2 minus x1. Whoops. Whoop. So we've got 11 over 4, which is exactly 2 3/4. So it's pretty close to the slope we got for secant line number 1, which we got 3 for that. And if you look at the two lines here, the green line and the blue line, they're not parallel. They're pretty close to parallel, but they're not. Down here, they're starting to get closer together at the bottom of the line. So we shouldn't expect to find the same slope because our lines aren't parallel with each other. When you look at the slopes of the secant line, you can see that maybe one of them is a better predictor than the other. So one of these secant lines is a little closer to what we want than the other. Let's go back up to our question. Draw 2 secant lines that you could use to estimate the slope of the tangent line when x equals 2. We did that. We did 2 secant lines that have centered themselves around the x value of 2. Calculate and record the slopes of those lines. Done. Then draw a tangent line. Okay, that's the hard part. The tangent line has to touch the graph at 2, 1. It has to touch there and nowhere else. So you're going to try and draw yourself a straight line here with a ruler where you're just skipping off this exponential graph at 2 and drawing a straight line through there. So press pause and give that a shot. So I've got my ruler here, and I'm going to try to get it right to that point, 2, 1, but nowhere else. So if I drew my line here, I'm kind of cutting through the curve there. This is going to be really hard to do. It's very hard to draw tangent lines. Usually we let a computer do it for us. We're just doing our best right here. So I'm going to angle my ruler up a little steeper move it in, maybe a little steeper still. That looks pretty good. So I'm going to draw my tangent line right there. So it's a little bit faint there, but we've got this orange line that is supposed to be my tangent line. And everyone's is going to be different because we're doing it by hand. It's just best we can do. So how do we get the slope of the tangent line? The slope of the tangent line, remember, is the instantaneous rate of change. If I can get exactly the slope of that tangent line, then I will know exactly how my function is changing when x equals 2. However, my tangent line is not right. I know that for a fact. I didn't do a perfect job with my tangent line. So there's a lot of errors already built into this. Even the red function I drew originally isn't perfect. So there's a lot of mistakes here, but we're just kind of going through a trial practice here. To find the slope of the tangent line, what we would normally do is we would use the point 2, 1 as our first coordinate to find the slope, but then we need a second point. So I would have to look at my orange line and somehow find a spot on that orange line that I could use for my second point. And that's pretty hard because none of them are passing nicely through the grid lines. So what we can do, because we have an equation, it's hard to tell exactly another point on the line other than 2, 1. So I'm going to sub into the equation to find one, the equation of the line. I'm going to go back up to my function. I had, my function is f at x equals 2 to the power of x minus 3. So I'm going to sub in really a value that's quite close to 2. I'm going to put 2.1. I'm going to try to find 2.1. So technically that won't be on my tangent line. That will be back on my red line. But since I don't have two good spots on my tangent line to use, this is what I'm going to do this time here. Now, if your graph does go nicely through, if your orange line goes nicely through a coordinate, and you say, oh, look at my orange line, it goes right through, I don't know, the coordinate 4, 12, okay, then you would use that, but mine doesn't. So I'm just going to go really close to this value of 2, but still on the red line. I'm going to calculate that, and I get f at 2.1 is about 1.287. So now I can use this coordinate here, 2.1 and 1.287 as my second coordinate, and now I can find the slope. So I'm going to look for the slope of my tangent line, and you're just using the same formula that we've always been using. So I sub those in, and I have 1.287 is my y value right here. This is my y2, this is my y1, sorry, x2. Subtract, and then the important coordinate that we're talking about all along is 2, 1. Then I have 2.1 subtract 2. That gives me approximately 2.87. So this estimate here is the best one so far. They're all really close, right? This I've got 3 for one of them. I've got 2 3/4, which is of course 2.75. So they're all very close to each other, but the tangent one should be the best one. So the instantaneous rate of change when x equals 2, this is our best option here. The slope of a tangent line is always going to be better than the slope of secant lines. This is our last slide, and I'm just showing you an animation of the graph that we just did. The blue curve is our exponential function, 2 to the power of x minus 3, and this is the tangent line going around that function. This is what the slope is, or the rate of change. It'll stop there at 2, stopping it there. There's my x value of 2. It stops at the x value of 2, and this is what the tangent line should have looked like. This isn't what mine looked like, maybe it's what yours looked like, but this is what the tangent line should have looked like. If I wanted to calculate the slope of this one, I could try to find, two coordinates. I might use this one right here. It looks like it passes through kind of the crosshairs of the grid lines nicely, and then I would use this. So all we did today was we looked at graphs, we looked at their tangent lines and their secant lines. You have questions to practice on this. There's a few textbook errors, so just make sure to take a look at the handout for that.